In homework 3.1, we're looking at 5.1, sorry, we're looking at differentiability. And this is going to be a condition that's important for a lot of things to hold true. There are things that are true when something's differentiable, but not true when it's not. And so we've got this function. We've got a piecewise function. This says that the function is this cubic polynomial when x is less than 0. So to the left of 0, we've got some sort of cubic polynomial, and then to the right of 0, we've got cosine of x, And we know that this part's differentiable because cubics are differentiable, and we know that this part's differentiable and continuous because cosine is continuous and differentiable. What we don't know is, does it meet up here and is it differentiable here? And so to be continuous, we just need those two parts to meet up. However, just being continuous doesn't make it differentiable. To be differentiable, the slope of the tangent line from both sides has to be the same. So in this thing I just drew, this would not be differentiable, whereas if it looked, like the polynomial ended here and then cosine began there, then it would be continuous and differentiable. So we're going to check a few things. Let's do D. F prime of pi over 2. So first we're going to find f prime. F prime of x is going to be a piecewise function, and to the left of 0 it'll be the derivative of this, 3x squared minus 6x, and the derivative of 1 is 0. And this will be when x is less than 0. This will be the derivative. The slopes of the tangent lines to the left are the slopes of the tangent lines of the cubic function. And the derivative of cosine is negative sine of x. And it used to say greater than or equal to 0, but we're just going to say it's greater than 0 because we actually, in order for the derivative to be equal to 0, it needs to be from both the left and the right side, and otherwise it's undefined. And so we're just going to leave a greater than sign there. And so now let's check f prime of pi over 2. So we need to know which part of the function are we on. It's this quadratic when x is less than 0, and it's this trig function when x is greater than 0. Pi over 2 is a positive number, so it's greater than 0. So we're on this part. So f prime of pi over 2, since it's above 0, is just negative sine of pi over 2. And you're supposed to know your unit circle, pi over 2. So here's 0. If you go all the way around the circle, that's 2 pi. Halfway around is pi, and half of that is pi over 2. So here's pi over 2 right here. Sine of pi over 2, sine is the y value, and so this is 1. So we have negative 1. Okay, let's do E. Is this function continuous everywhere? Justify your answer. When we've got this justify our answer, we need to prove that it's continuous. And so we want to know if it's continuous everywhere. Well, we don't actually need to worry about any of the points except for x equals 0. And the reason is because cubics are continuous everywhere and cosine is continuous everywhere. We just need to see, do they match up? Do they have the same value coming from the left and the right? And remember what we need to do is we need to do the limit to prove it's continuous. We need to do the limit as x goes to 0 from the left. And we need to see, does that equal the limit as x goes to 0 from the right of f of x? And that needs to be equal to f of 0. So those three things all need to be the same. So the limit as x goes to 0 from the left, we just plug in 0 into the left one, direct substitution, and we get 1. The limit as x goes to 0 from the right, we plug in 0 into the 1 as we come from the right, and that's cosine of 0. Cosine of 0 is 1. And f of 0 is just the value at 0, and that is also 1. And so f is continuous everywhere. This is an important sentence. On the AP exam, this sentence needs to be almost exactly like this. F is continuous everywhere because limit as x approaches 0 from the left of f of x, you need to write it exactly like this, equals the limit as x approaches 0 from the right of f of x equals f of 0. And those are all equal to 1. And polynomials and cosine are continuous everywhere. So there aren't any points anywhere else we're worried about it not being continuous. We need to have checked that, and we need to check and make sure the limits match up. All right, let's do number 10. I'll do this in a different color just so this doesn't blend in. We've got another piecewise function. F of x is this guy when x is this cubic when x is less than or equal to 2, and it's this quadratic when x is greater than 2. So there's some graph, and at 2 it splits over from being a cubic to a quadratic. And we want to determine the values of k and b to make the function differentiable everywhere. Okay, so when we approach a problem, we really want to be able to read the problem and think about the clues it gives us. To be differentiable everywhere, well, the first thing I think is cubics are differentiable everywhere and quadratics are differentiable everywhere. So we only really need to look at when x equals 2, is it differentiable? The other thing we need to know is that if a function is differentiable, it also must be continuous. Okay, so for this function to be differentiable, it needs to be continuous at x equals 2, and the derivative must be 2. And so we do some limits. The limit, to find if it's continuous, this is checking continuity. To check if it's continuous, we need to do the limit as x approaches 2 from the left. See, is that equal to the limit as x approaches 2 from the right? And see, is that equal to f of 2? So as x approaches 2 from the left, we'll be using the function that's less than 2. This is the function, and we can just do direct substitution. 2 cubed is 8. 2 times 2 squared. 2 squared is 4 times 2 is 8. 8 plus 8 is 16. The limit as x approaches 2 from the right, we're going to be using the function as it comes in from the right. And so we're going to get 2 squared, which is 4. 4 times k is 4k, plus b. So we get this equation. 4k plus b must be 16. Great, well, that's good. But we can't find what k and b are because there are 2 variables. And in order to solve a 2-variable equation, we need 2 equations. We're going to need to make a system of equations. And that's where this differentiable part is coming in. Not only does it have to be continuous, but we know from the differentiable part that the limit as x approaches 2 from the left of f prime of x has to equal the limit as x approaches 2 from the right of f prime of x. And so the derivative from the left is 3x squared plus 4x, and evaluated at x equals 2, we can just do direct substitution. We get 3 times 4 is 12, 4 times 2 is 8, so we get 20. And that needs to equal, okay, the derivative from the right, as we approach from the right, the derivative of k and b are constants. They're like, you can think of them as like 7 or 3. The derivative of a constant times x squared is going to be 2 times that constant times x. The derivative of x squared is 2x times the constant. The derivative of b, the derivative of a constant, is 0. And when we plug in 2 in for x, we'll get 2k times 2, which is 4k. So 20 equals 4k. This is a particularly easy system of equations because we can just solve for k. K is 5. And once we know k, we can plug it in here. And since k is 5, we get, I'm going to rewrite this equation over here with k plugged in. We get 16 equals 4 times 5, 4 times k. K is 5. 4 times 5 is 20, plus b. And so b is negative 4 when we subtract 20 on both sides. So k is 5, negative 4 is b. After doing a long problem like this, I like to reread and make sure I've actually answered the question. Determine the values of the constants k and b. K is 5, b is negative 4. To make the function differentiable everywhere, these are those values. All right, on the back, you've got some old stuff from earlier in the semester. You've got a final exam coming up in not too long. It's going to have everything we've done all year long. The AP exam is going to have everything we've done all year long. The first section has some limits. The next one, I want you to do the derivative of this. This is clearly going to be a quotient rule. Then we've got this table where you've got these weird derivatives to do. None of them should be tough if you know what you're doing. If you need any help on these review things, make sure you come in and get it because this stuff isn't going away.